My name is Richard Smith. I'll moderate today. I'm the Vegetable Crop Wheat Science Farm Advisor here in Monterey, Santa Cruz, and San Benito counties. And this is our third and final series on practical training on nitrogen management and organic production of vegetables and strawberries. And we've had two sessions with excellent presentations, giving us kind of all the background information on mineralization from soil organic matter, from compost, from cover crops, from organic fertilizers, and from irrigation water. And today we're going to attempt to put all this information together. And we're going to have three presentations, one by Joji Muramoto on fertilization of organic strawberries. I'll give the second presentation on fertilization of our organic vegetable production. And then we'll have a third presentation by Joji on new frontiers in organic fertilizer management. So stay tuned for that one. That ought to be very, very interesting. And then we'll wrap up and be done at 11 o'clock today. So thank you all very much for coming. And without any further ado, I almost forgot. Para nuestros hispanohablantes, si necesitan traducción, sigue al fondo de la pantalla y se encuentra el enlace para traducción al español. La interpretación es por Diego Chelas hoy. So, gracias por venir. And so we will get started. Joji, take it away.
All right, thank you very much, Richard. Good morning, everybody. And yeah, I'm pleased to be here to talk about nitrogen management in organic strawberries. Can you hear me okay?
Sound great.
Yes. Okay, thank you. All right, so here's an overview of today's talk. First, I'm gonna talk about the very basics. Let's just to be on the same page. Nitrogen management basics, roles, nitrogen roles in plants and nitrogen forms in soils, and the concept of synchrony. Then talk about nitrogen uptake by organic strawberries and nitrogen supply for organic strawberries. And some tools for nitrogen management in organic strawberries. And finally, I'm going to talk about briefly field trials I conducted with my colleagues, use of high carbon amendment to reduce nitrogen loss in broccoli strawberry rotation. Okay, let's get started. So the very basic, why nitrogen is so important? Because plants need nitrogen for many different processes like photosynthesis and biomass structure, metabolism, energy production, reproduction, all requires nitrogen. That's why when it's deficient, leaves tend to show yellowish color due to lack of chlorophyll, and in smaller plants and lower yield. But if you apply too much, leaf color tends to become very dark greens and larger plants and become susceptible to diseases. Nitrogen in the soil can be divided into organic form and inorganic form. And inorganic form consists mainly of ammonium nitrogen and nitrate nitrogen. And about most of the nitrogen in the soil are organic form. And inorganic form is very small part of it. And the bad news is the majority of organic nitrogen is not plant available. And only small percentage inorganic nitrogen is plant available form. But the good news is part of the organic nitrogen can be transformed to inorganic nitrogen through the process called mineralization, first to ammonium, then to nitrate through the process called nitrification. Both mineralization and nitrification are biological processes. mediated by soil microbes. So because of biological processes, it's affected by environmental factors such as soil moisture and temperatures. Daniel Geisler talked about it 2 weeks ago. Also, this charge difference between ammonium and nitrate has a very significant implication. As you know, majority of soil particles like clay particles or organic matter has a negative charge. So ammonia can be held electronically, but nitrate repel to soil particle. So nitrate move along with water and with leaching susceptible. Another important and very common sense concept is synchrony, which means matching nitrogen supply with nitrogen demand of plants in terms of amount and timing. This figure shows the nitrogen demand by plants, this peak, and this is the nitrogen supply, darker one. And in this case, it shows the asynchrony. Synchrony is not realized because nitrogen supply is too early than nitrogen demand. So this early part can be lost by excess irrigation or rain event. The goal is to match in terms of amount and timing of nitrogen supply with nitrogen demand. This is important for efficient use of nitrogen resources and protecting ground and surface water from nitrate contamination, reducing nitrogen fertilizer cost, and good fruit yield. So to realize synchrony, first we need to know the plant demand, plant nitrogen demand. How much nitrogen is absorbed, when, and how much. So let's take a look at it. So this is work I did with my colleague early 2000 about the nitrogen uptake by organic strawberries. This is an average of 4-year data, and then yield level is about 40,000 pounds per acre. It's not very high, but that is what it is, what it was. As you can see here, it's very interesting nitrogen uptake pattern. The x-axis is weeks after planting, so this is the planting date. The first almost 20 weeks, so 4 to 5 months, nitrogen uptake is really slow. But once harvest starts, this red part is harvested fruit. It starts to absorb nitrogen in a very consistent manner. In this case, 3 pounds of nitrogen per acre per week. At the end, total nitrogen uptake was about 100 pounds. And as you can see here, half of the nitrogen went to harvested fruits, and the rest went to the rest of the plants. Similar research was done in conventional strawberries with much higher yield. The yield is average yield in this case, 73,000 pounds per acre. This is marketable yield. And then it was studied in Santa Maria and Watsonville. And again, nitrogen uptake until harvest season is very low, only like 20 to 40 pounds. And this doesn't show the planting date, but it's like very far planting date. And once harvest starts, consistent uptake take place. And then due to higher yield, number of uptake is much higher too, 6 to 8 pounds per nitrogen per acre per week. And putting it all together, I came up with this table. This table shows the amount of nitrogen uptake during harvest period for different target yield, from 40,000 pounds per acre to 80,000 pounds per acre. This is marketable yield. Assumptions are cover rate is 20%. And each ton of fruits contains 2.2 pounds of nitrogen. And nitrogen uptake by fruits versus shoots ratio is 1:1. And harvest period is from April to September. So if you have a more yield, obviously have more nitrogen uptake. And interestingly, the average nitrogen uptake during the harvest period per week, you can almost remember those numbers because it's pretty simple relationship. 40,000 target yield is 4 pounds per acre per week. And 80,000 pounds target yield is 8 pounds per week. So this is kind of interesting and informative data you can use. And you can, of course, adjust the cover rate and other factors based on if you have data. Nitrogen uptake of strawberry is very unique compared to vegetables. Last week, Patricia and Margaret shows the nitrogen uptake by tomatoes here. And Richard's gonna show after myself, nitrogen uptake by broccoli. It's so different. First 4 months, only 20 to 40 pounds per acre of nitrogen absorption. It's very slow. And then steady nitrogen uptake, 4 to 8 pounds per acre per week for 6 months or even longer. So how we can provide nitrogen for this kind of nitrogen demand? How we can realize synchrony of nitrogen supply and nitrogen demand in this case. So let's take a look at the nitrogen supply part. Traditionally, organic growers concentrate on soil organic matter management as basis for organic production program. So let's take a look at the contribution of soil organic matter in nitrogen provision. This is from Daniel's presentation 2 weeks ago. He simulated the nitrogen release from soil organic matter in 2 different scenarios. Organic matter content 1.5% case and 3.0% case. These numbers are pounds of nitrogen per acre per month from top foot of soil. Strawberries in these regions usually planted in November. So I focus on the early part first, November till March, this pre-harvest season, which as I showed you, nitrogen uptake during this period is only 20 to 40 pounds per acre. And how much nitrogen can come from soil organic matter? For 1.5% scenario, it can provide almost 20 pounds. For 3%, almost 33 pounds. So it can provide significant amount of nitrogen from soil organic matter. How about from irrigation water? Michael Kahn last week talked about nitrate in irrigation, nitrogen contribution from irrigation water. And according to Mike's survey, typical irrigation rate during pre-harvest season is about 12 inches. So using that number and 2 different scenarios, nitrate nitrogen content, 5 ppm and 10 ppm, and put into the Mike's formula, 5 and 12 inches, and the conversion factor 0.23. So in the case of 5 ppm nitrate nitrogen content concentration, it can provide 14 pounds of nitrogen per acre. And for 10 parts per million, 28 pounds. So, especially this pre-harvest season, not all water are irrigated through drip system. Some parts, or sometimes majority was sprinkled using the sprinklers. So not all those nitrate are used by plants. But regardless, given the fact that such a low nitrogen requirement throughout the first pre-harvest season, it is obvious that not much pre-plant nitrogen is necessary for strawberries. Last week, Patricia and Margaret shows this chart and then showed how much nitrogen becomes plant available from different kinds of organic fertilizer and compost. You might remember yard waste compost doesn't release much throughout the, for the 12 weeks incubation period. So probably not for the entire season, but gradually, as these are applied, soil organic matter content can be increased and mineralized slowly. For the rest, mineralize pretty fast. Something like guano peaked only 6 weeks after 42 days. And some becomes almost a plateau after 12 weeks. So how can we use this kind of organic fertilizer for organic strawberries? How can we synchronize nitrogen supply with this kind of organic fertilizer to organic strawberries? To examine how to do that, I'm gonna use the hypothetical scenario of a feather mill. Pretty much, pattern is pretty much similar. So let's use one example here. Feather mill, typical nitrogen content 12%. And according to this, plant available nitrogen is 60%, a little higher than 6%, just to make it simplified. Let's use number 60 for now. And then let's use the 60,000 pounds marketable yield scenarios. This is a target yield. So the total nitrogen uptake is going to be 165 pounds per acre. So to provide this amount of nitrogen using feather mill, you need to apply about 1 ton per acre of feather mill. 1 ton of feather mill, 12%, total nitrogen content is 275 pounds, of which only 60% becomes plant available form. So 1 ton can do that to match the amount. But is this a good approach? That's a question. Again, last week, Margaret and Patricia showed this chart. This is tomatoes, organic tomatoes nitrogen uptake and the nitrogen provision from different sources. And as I showed the picture or figure in synchrony, this part, front part, is available for loss if excess irrigation water is applied or if some rain event happens, because plants doesn't need this nitrogen up front. In that lens, this feather mirror approach is quite risky because strawberries' low nitrogen period is much longer than tomatoes. On top of that, this low nitrogen uptake period takes place during winter time, which we normally have some rain events. This is actually actual rain event data from Pajaro Sims Station, 2019 and 2020. And then when that happens, those available nitrogen, mostly in nitrate form, can be lost by leaching or just runoff loss. So this is not good for your pocket and then to the environment. This is a common challenge for pre-plant application-based approach fertility management in organic strawberries. All those organic fertilizers and even cover crop decompose and mineralize too fast for strawberry nitrogen uptake patterns. And here I showed 2 different lines of nitrogen uptake. And the first one is actually for Southern California, like Oxnard area. where temperature is much higher. So plant nitrogen demand is much more steep and can use more nitrogen in the early stage. So pre-plant nitrogen fertilizer can be more effective and efficiently used in warmer regions like Southern California. But for Northern California region, again, nitrogen uptake for the first 4 months is very slow and tiny. So it's very difficult to synchronize nitrogen supply just with pre-plant fertilizer. So that's the reason we need to use in-season application of fertilizer to make to synchronize nitrogen supply and nitrogen demand in organic strawberries. This is going to be very important. And how to apply in-season nitrogen for organic strawberries? Well, it's all plastic mulched, so band application is not practical. So the only way is fertigation. Use a liquid organic fertilizer. But liquid organic fertilizer has one common issue. As you apply multiple times, it tends to clog the drip tapes. It's a common issue. So some growers set up double drip lines from the beginning, on the onset. When clogs happens, you just switch the drip lines. Or these days, water-soluble organic fertilizers are available. So that's another option. Hydrolyzed soy protein. But the issue is the price. I borrowed this chart from Richard. He made it 2 years ago. So this price may be not accurate anymore, it might be more expensive. But the point is, the top two are typical liquid organic fertilizers. Fish cone base or fish base. It costs about $12 per pound of nitrogen, which is almost 3 times of dry fertilizers nitrogen. And a water-soluble hydrolyzed soy protein is further more expensive than typical organic liquid fertilizer. So that's something you have to think. Now, how much we should use those liquid organic fertilizers? Again, this is the nitrogen uptake per week during the harvest period with different target yield, right? So we can apply just this, but let's take a look at about how much nitrogen can come from soil organic matter and irrigation water, and how much we can save the amount of supplemental fertilizer. Again, back to Daniel's data. So let's focus during the summertime, harvest time now. So 1.5% scenario, we can provide 1.5 pounds per acre of nitrogen per week. That's another easy to memorize number. And if the soil organic matter increase to 3%, it can provide almost 3%, right? This rounding is a little bit lower. So yeah, soil organic matter has a lot of effect, improving soil health in many ways, but it also can play a very important role in providing nitrogen to organic strawberries. How about irrigation water? According to Mike's survey, typical irrigation rate during this time is 18 inches. And then in the 5 ppm scenarios, can provide about 1 pound per week, and 10 ppm, 1.6 pounds per acre per week. So this is a significant part. depend on soil organic matter content and nitrate content in your irrigation water, you can adjust the amount of nitrogen you apply through fertigation. Also, very important tool and very useful tool in nitrogen management is tissue test, total nitrogen of leaf blades. You supposed to take a young matured leaves, not just petioles, remove petioles and just collect like a triplet, leaf blades, and then analyze total nitrogen. There's an optimum range. There are optimum range established for different stage of strawberry, early flowering, early harvest, main harvest. So take leaf samples and analyze it. This is a very good way to confirm if plants has enough nitrogen. Some growers use petiole analysis, or for nitrate petiole analysis, but that number is highly variable compared to total nitrogen in leaf blades, and maybe less reliable for organic system. And also soil nitrate test can be used too, especially if it's combined with tissue total nitrogen test, it can be very useful. Typically 10 to 25 per million in topsoil soil is a good range. But as long as tissue tests indicate plants has enough nitrogen, lower number than this range is fine, just fine. Now I'm going to talk about tightly coupled plant soil nitrogen cycling after research talk, but some nitrogen can be really rapidly absorbed by plants. Like last week, Michael was talking about, irrigation nitrate in irrigation water does not necessarily increase soil nitrate pool because it can be absorbed really efficiently by plants. Same thing could happen for soil organic matter mineralization. It might not increase the soil pool, but still can be used by plants when plants are active. So which is a good thing. In summary, nitrogen uptake of strawberry in the first 4 months is low, only 20 to 40%, 20 to 40 pounds per acre, and followed by a steady uptake, 4 to 8 pounds per acre a week throughout the harvest period. So pre-plant nitrogen, I would suggest to apply just not moderate rate, 50 to 75 pounds per acre, and to avoid the nitrogen loss to the environment during rainy winters. And it turns out to be warm and dry winter, you can start fertigation early. The beauty of fertigation is you can start anytime. In-season nitrogen applications are a very important part of nitrogen management in organic strawberries. 4 to 8 pounds per acre per week during the harvest season, adjusted according to the target yield, soil organic matter content, nitrate content in irrigation water, and tissue total nitrogen test. And fertigation of liquid organic fertilizer, you can use common organic liquid fertilizers plus drip line approach or hydrolyzed soybean protein fertilizer approach. The important thing is soil organic matter and irrigation water can be significant nitrogen sources for organic strawberry. Now, I'm going to talk about one field trials. And broccoli strawberry rotation is a common rotation among organic growers because broccoli residue incorporation can reduce the Vertium dariae, lethal pathogen for strawberries, the population in the soil. So it's a good rotation. But as we learned from Daniel's talk 2 weeks ago, broccoli residue has very rich in nitrogen and CN ratio is about 10. So it can release a lot of nitrogen after being incorporated. And I just did monitored. This is the actual data of how much nitrogen was actually released after broccoli incorporation and fertilization in a particular field. And this data, black line shows the soil nitrogen dynamics, nitrate and ammonia in top foot soil and in the pounds per acre unit. And then red line shows the nitrogen uptake by strawberries. And in this case, residual inorganic nitrogen is quite high. So baseline was quite high. But by incorporating broccoli residue, soil nitrate level was further increased at 250 pounds in top foot soil. It's a lot of nitrogen in there. And that's the time of planting, actually. And again, plants doesn't need nitrogen for the first 4 months, not much at all. And then rain event came. All the nitrates actually went somewhere, which is not a good thing. So this is a good example of asynchrony and bad example of synchrony. But this is not the particular problem of organic production. In fact, if it's conventional system, it could be worse because broccoli biomass is much larger. And this is not just California problem either. Any in the world, like growing broccoli has the same problem. Broccoli, cauliflower, so forth. And I found a couple series of studies actually in Europe and Canada using high carbon amendment, like straws, or in this case, ground almond shell or so forth. C2N is very high, so it actually immobilizes nitrate that are released from broccoli residue back to organic form. And this seems to reduce nitrate during the wintertime. And so we wanted to try in California, and Richard and myself started the project 3-4 years ago. And I did one for strawberries in 2017 and 18. And it shows very promising outcome. It reduced the nitrate leaching potential and also increased the yield in this particular case. And it was very heavy soil in the field, but we want to try again to see if that works again, reproducible. So this case, it's a large scale demonstration, non-replicated trial in Watsonville. This time is sandy loam to loam soil. Again, organic broccoli strawberry rotations. And all the field previously broccoli and residue incorporated, but 3 acres part, we applied ground almond shell, 6 tons per acre. And we use adjacent field as a control. And then this time, yield was not different. It's almost very close, identical. Little bit lower in almond shell, but only 2% difference. The effect of almond application to soil nitrate dynamics are very, substantial. So this is the control nitrate changes. Its peak is 30, so not too high, but down and like this. And then by applying almond shell, this is the top foot nitrate, the peak shifted 3 months, interestingly. And these are precipitations, actual nearby CIMIS station. This is very important because this is a nitrogen, fruit harvest curve, which represent measure nitrogen uptake time of strawberries. So by applying almond shell, peak nitrogen release, well, once immobilized here, and then re-release when plants need nitrogen, so which is a good thing. And I tried to estimate how much nitrogen was lost during this storm event. The peak went down here in untreated control, and then, almond shell plot like went down like here. we took 3 feet of soil, top foot, second foot, and third foot. And then for the 3 feet depth, using 1.3 bulk density, it's estimated that over 200 pounds of nitrogen existed in the 3 feet depth in control, whereas almond shell plot was just a half of it. This is March when the topsoil nitrate peaked. Months later, April, after the couple of storms, number went down, control down to about 100 and the almond shell about 50. So the difference shows the nitrogen loss. Small part of it was absorbed by plants, but roughly 60% of nitrogen loss reduction was accomplished by using almond shell. So this time, although it didn't increase the yield, but it didn't decrease the yield either by almond shell 6-ton application. And it changed the nitrogen dynamics quite significantly. Immobilized broccoli-derived nitrogen and changed the peak, shift the peak, delayed the peak for 3 months and make it more synchronized with nitrogen demand with strawberries and reduce the nitrogen potential leaching. We call apparent nitrogen loss. But the problem is the cost of almond shell. This time, this almond shell was donated from Almond Board of California, but we have to take a look into the cost of this approach more economically. If we can economically do this approach in the strawberry production system. So I thank my collaborator for this particular project and happy to answer any questions.
Hey, Joji, we've got a couple of questions for you. How much nitrogen can one expect from ASD rice bran at 8 tons per acre to contribute to the nitrogen needs throughout the season?
Yes, that's a very good question. I didn't show that in the slide today, but rice bran 8 tons can provide, rice bran is like average nitrogen content 2%, the CN ratio about 20, and it shows very interesting mineralization pattern. Yeah, email me, I can send you the data, but mineralization rate is about 20 to 25% in first 6 months. So if you apply 8 tons, it provides roughly about 100 pounds of nitrogen for the first 6 months. So it provides good amount to the early part of it, but the rest, after the 6 months, you have to apply supplementary fertilizer.
Okay, very good. And then here's a question. How is the almond shell immobilizing nitrogen?
How? Yes, so almond shell's C/N ratio is over 70. So it has a lot of labile carbon in it. And then microbes trying to decompose, use that carbon to digest. They also need protein to form their biomass. So, and there's, if there's an excess nitrate in the soil, they use it to make their own body. That's how immobilization takes place.
Okay. And kind of following up on that, Joji, does incorporation of green waste compost prior to bed shaping that has, kind of a high C to N ratio as we've seen in those graphs from Patricia and Daniel, with a high C to N, would it work similarly to delay the peak N release? Yeah,
that's what we're doing, right, Richard? Yeah, we're trying to demonstrate it right now as we speak, running experiments right now. Yeah, almond shell is, itself is not expensive, but the grounding cost and also transportation cost. So if we can use locally available high CN compost, that's much more affordable and cheap. And that experiment is taking place right now. So Richard will report you maybe this fall or next spring.
Yeah, okay. All right. And then this will, I guess, will be our final question. It says, hey, Joji, I know you and Richard posted a blog on the almond hulls and lettuce trial. Did you post the strawberry one on a blog or has it been published in a peer review journal?
Yeah, not yet. I'm still working on it. But you know, this experiment's just finished, and we came up. Turns out to be very interesting and effective. So I will work on the publication very soon.
Okay. Actually, I didn't see there's more questions down here. Let me see how many more we can get through. We're going a little bit over time, but not much. We started a little bit late. Here's another one. How much information about whether strawberry growers reduce nitrate leaching by carefully managing drip irrigation during the winter?
Yeah, that's very good. Well, Michael talked about drip irrigation system last week, but basically, you know, try not to apply too much pre-plant fertilizers, and then over irrigation is not good for nitrate management at all. So, and then during the winter time, depend on the weather, but if you have typical rain, you know, you don't need much irrigation. And then the question is about the sprinkler or versus drip irrigation. Yeah, drip irrigation is more efficient, but some growers prefers sprinkler to establish plants. So when you use sprinkler, I think it's very important not to apply too much pre-plant nitrogen. It works like rain.
Yeah, okay. Here's an interesting one. Any thoughts on foliar feeding with soy, the hydrolysates of soy?
Yeah, I never tried that. So that's something we have to examine. Richard, have you done that for vegetables?
For vegetables, yeah. You know, typically you can't, well, I never tried the soy hydrolysate. We were just using regular, you know, conventional fertilizers, but you can only put so much on because they're very salty. So that's the problem in vegetables have such a high uptake rate. So strawberries is something entirely different. And then that material is something entirely different.
Yeah, that's something probably should try and yeah, test it. Yeah, foliar application, I didn't mention at all. But the organic system material has been very limited. So that's something new and worth testing, I think.
Yeah. Okay. And then final question. With the almond shell application, it seems like you would potentially be able to save money on nitrogen applications due to the timing on the release of nitrogen. That's a question.
Yes. Yeah. That's the next step, you know. Basically, you know, the next step is you know, change the fertilization rate according to the soil nitrate level in case of almond shell application. Yes. So we might be able to save some in-season application because of supply from almond shell. So that's a possibility.
Okay. All right, Joji. Well, maybe we'll have some time at the end to answer more questions, but we kind of got through all the ones that were in the Q&A right just then. So now we will move on to Richard Smith, who's going to talk about fertilization of organic vegetables. And welcome everybody. I wish I could see everybody. I saw your names there, but welcome to this meeting. And very nice talk by Joji, and appreciate that. And hopefully this will be informative, but I'm going to talk about fertilization of organic vegetables, and going to try and pull together, some of the things that we've heard from the prior speakers. And as you know, we've heard talks about mineralization of nitrogen, plant available nitrogen from soil organic matter, from various amendments, organic fertilizers, as well as nitrogen from irrigation water. And, why are we so concerned with getting this right? Well, first of all, as Joji showed that slide, the economics of using organic fertilizers are quite expensive. So we have to be as judicious in their use as possible, but then also, protecting the groundwater from excess nitrate leaching. And, the organic operations are going to be subject to the A and a minus R, applied minus removal regulations that are in the current version of Ag Order 4.0. And so the organic growers are going to need to be able to, fine tune their operations, and then improve nitrogen use efficiency, and then also be in compliance. And one of the things that we run into, it's very difficult to precisely apply nitrogen or in organic systems. And I'll try and shed a little bit of light on how we can try and improve precision. And this will revolve around really you as growers, the experience and skills that you develop in your growing. That's very important. We don't want to emphasize that, because that is probably as important as anything. And then we'll talk about soil nitrate testing, and then how the plant growth characteristics affect all those sorts of things. But a lot of what I'm going to talk about is over the years, I've done different studies on organic. I've worked a lot on conventional, but in the last 4 years, I did some studies with large scale organic farms here in the Salinas Valley, 28. We evaluated at least 28 blocks, and in these operations, the growers nearly exclusively use dry organic fertilizers. Very little of the liquids were used, and in that information you just saw from Joji, you can kind of see why, because of the economics and the ability in a vegetable system to be able to get in there. There's not the plastic mulch and so forth that becomes an impediment to applying materials. So they're able to use them, and they do. And over 20 of these blocks, we looked at the nitrogen budgets and balances, and what we saw was that in 20 of them, more nitrogen was applied than the crop took up, and about 205% more nitrogen was applied than the crop took up. However, now if you remember from last week from Patricia's talk, when we account for how much of that nitrogen, the nitrogen that's in that organic fertilizer is actually mineralized into a plant available form, then it turns out that only about 85% of the amount of the nitrogen that's taken up by the crop was supplied by the fertilizer. Well, I think you know why. That's because not all the nitrogen in the organic fertilizers is mineralizing. And so if we talk about like this 442, which was the most common one, Patricia threw out a value, about 50 to 60% of the nitrogen in that material would mineralize over the course of the crop cycle. And so that's one factor. But the other factor is in some of the crops that we're growing here in Salinas, there's a lot of use of top dress. And that's just dropping the fertilizer on top and then using sprinkler irrigation to incorporate the nitrogen. And as Patricia showed last week, that also that reduces further. If only 50 or 60% is going to potentially mineralized. If you drop it on top of the soil, and then that drops you down another 30 or 40% in terms of what becomes available. That's part of the reason that we see that the organic farmers are actually not applying what the crop is taking up. And so we really need to understand, this is a basic question then in fertilizing any crop. How much nitrogen does that crop need? And then is your nitrogen, what is it supplying? And so I just want to show you this. This is a starting point. This is a chart from this book that everybody needs to get. Everybody who's involved with nitrogen management, organic and conventional, either way. It's a new book, Efficient Nutrient Management in California Vegetable Production by Tim Hartz. It was published in 2020. And he's got these numbers on crop uptake. And there's a large number. I showed a number of them that are in the book, but we're going to focus on spinach and then full-term lettuces and broccoli in this discussion. But you can see the spinaches take up about 90 to 130 pounds, lettuces 120 to 160, and broccoli 250 to up to 350 pounds of nitrogen in the above ground biomass of the crop. Now, when we look at fertilizer programs, what I want to show you here is some data. This is from the Central Coast Regional Water Quality Control Board from 2017, and growers are reporting their nitrogen use for different crops. And what we have here's different amounts of nitrogen. Here is down here, here's 100 pounds. Here's 200 pounds, 300 pounds. And in this shaded area right here, this is the 90 to 130 pounds that we have measured many, many times in spinach crops in the Salinas Valley that's taken up. And this is what the crop is taking up. All these blue bars show you an amount that was applied by different growers. And what you can see is that there's quite a number of growers that are applying more than the crop's taking up. And this is exactly what the Regional Water Quality Control Board is trying to work with the growers to try and shift this curve to the left, get growers applying more closely to what the crop takes up. But the point of this is also just to show you kind of a typical amounts that are applied. And you can see, a lot of times you'll see numbers of 140, 160, 180. These are very common amounts that are applied. In the organic farms that we've worked with in our project over the last 4 years, the organic programs, growers are putting on about 120 to 210 pounds of nitrogen. That's the range that we saw. 160 pounds per acre was a very common amount. But if you look at how much was actually mineralized, it ranged from 36 to 126 pounds per acre. And part of that depended on, of course, the material they're using. Mostly they're using a material like 442, but they're using some others. And but a lot of it's top dressed. And so then that's why you'll see these numbers actually coming back actually quite low in relation to what the crop is taking up. Now, just talk a little bit about the growth characteristics of a crop like spinach. Spinach, baby and teenage spinach, those are two commonly harvested clip spinach types that are grown here. They'll take up 80 to 100 pounds of nitrogen. That's because they're smaller when they're harvested. And then whereas something like bunch spinach will take up about 130 pounds of nitrogen, that's because it's bigger. But you lay it all out on this curve and you'll see that, as Joji mentioned, for strawberries, spinach is the same thing, except that everything happens much quicker. But like for the first 2 weeks, there's very little uptake of nitrogen. And then from starting at 2 weeks until harvest, the uptake of that crop it averages about 6 pounds of nitrogen per acre per day. So that's quite a bit of nitrogen. And it's, it's much higher than what Joji was referring to in strawberries. And that's because it's a different crop, and it's got a different crop cycle, and it's much more demanding. Now, where is it taking that nitrogen up? Well, we also looked at roots of different crops, but we looked at spinach, and what we see, the deepest roots at harvest, around 30 days after planting, are down around 16 or so inches. And then what we've also been able to determine by looking at the nitrogen uptake profiles in those soils, we saw that really most of the roots, we didn't really measure the roots, although we did a little bit of that, but we noticed that most of that nitrogen is coming out of a narrow band about 4 to 12 inches deep in the soil. That's where the nitrate is being extracted. And so one of the tricks with a crop like spinach is keeping the nitrogen in this very narrow band in the soil, not pushing it. And this is where irrigation management becomes absolutely critical for a crop like spinach. And so one of the things that we've been working with conventional growers is using measuring the pool of residual soil nitrate in the soil. And the thing that's nice about that pool of nitrate is that it integrates the nitrogen that comes from all these processes that we've been talking about over the last 2 weeks. So mineralization from organic matter, from crop residues, from fertilizers, compost, and so forth. And so this testing soil nitrate is the key tool that's used in conventional. So then the question that we were trying to answer is, could it also be a key tool for organic? And so when we use this tool, 20 parts per million nitrate, depending on the density of the soil, is about 70 to 75 pounds of nitrogen per acre. That's a number you can kind of relate to. That's a very common number in terms of amount of nitrogen that people want to apply in like a top dress or a side dress operation. And it's sufficient to keep the crop growing for 1 to 2 weeks. And so typically what you'd like to do is do this test just prior to a fertilization event to know how much nitrogen you need to add. So if you have 20 parts per million in the soil, you can either forego a fertilization or reduce a fertilization. And in conventional systems, this concept works very well. The problem in organic is that organic fertilizers, as you know, they take time to mineralize and to release that nitrogen. And for fast maturing crops such as spinach, this is very challenging. So then this test would have to be done well in advance of the need to allow sufficient time for fertilizer to mineralize. And you can't do it later in the crop cycle. It's just too late because there's not enough time. The crop's growing too fast, and the fertilizer takes time to release. But if you're interested in this idea, you can go on the Salinas Valley Ag blog and just type in details on the nitrate quick test, and there's an article there that'll explain this whole procedure. But as I mentioned, probably spinach is the most tricky because it's a fast growing, it's shallow rooted. Of course, it needs to have a good amount of nitrogen in order to look good. It's got to look good. We're growing it on 80-inch beds with high plant populations and with exclusive use of sprinkler irrigation. There's no drip currently being used. It's being experimented with, but it's not being used. So the irrigation system has limitations in terms of the efficiency. But I want to show you just a couple of trials. I won't beat you over the head with a bunch of data on this, but this is very interesting. There's 2 examples I want to show you. Here's one on a clay loam soil, And so what we were looking at then is we put, here's the fertilizer treatments. Here's the grower standard was 160 pounds. And then we put on smaller amounts at planting and then at listing, that's bed formation. And in order, and the reason is because this soil had 18 parts per million of nitrate nitrogen at planting. So that's a pretty good amount of nitrogen that's sitting there. And so then the question is, could that amount suffice for part of the fertilizer that we're planning to put on? And that's why we cut these fertilizer rates in half. And then, but you know, if you look at the actual amount of nitrogen that was going to mineralize from these applications, these listing and planting, you see the listing one was putting on, was mineralizing about 52 pounds, and then the planting was 32. And you might say, well, why is that? It's the same amount of nitrogen. This is an incorporated application. It's listed into the bed. It's folded into the bed. And so it's actually, and this is a top dress. And that's the difference in nitrogen. And the bottom line is, though, that none of these yields are significantly different from each other. They're all about the same. And what we see is that in this example, that this testing for the soil nitrate on this soil worked well. We were able to cut the fertilizer rate by 80 units of nitrogen. And we did not suffer a yield reduction in yield. This is on a clay loam soil. But if we go to a sandy loam soil where we did the same exact kind of thing, we put on 80 pounds and 160 pounds, both at planting. And this soil actually had 28 parts per million, which is even more. But what we see is we had a significant reduction in yield. So by putting on a smaller amount, because what we think is happening, although we didn't measure it, but what we think is happening is that there were probably more leaching at this site. And so even though we had 28 parts per million, that's at planting, and then you put on all that germination water and on that sandy soil, and then we lost some of this. And so it was not able to substitute for, so that you had to put on 160 pounds in order to get optimal yield. So the bottom line is then for a crop like spinach, high nitrogen demanding and shallow rooted, it needs that robust amount of nitrogen fertilizer in the root zone for the last 2 weeks of the crop cycle. These soil tests can be useful, but the problem is you have to do them at pre-plant or at planting. Those are, you have to do them early. And then if you have any leaching following doing that test, it might mislead you. And so that's something I think we still need more research on, but it was interesting that, you know, that we can, there's some evidence that we can use nitrate testing, even on a crop like spinach. Now, what I wanted to talk about now are just a couple of other crops that are not quite as demanding as spinach and that grow a little more reasonably and so forth. And one here, just one little trial I wanted to show you that we did on lettuce, on leaf lettuce. And leaf lettuce grows, you know, it's got the same pattern as spinach, you know, in the last, the first 30 days, you know, because it's got a life cycle that's about twice as long as spinach, so about 60 days instead of 30. And it takes up about 3 pounds of nitrogen, 3 to 4 pounds of nitrogen per acre per day during that peak period starting from 30 days till harvest. Its roots are a little bit deeper than spinach and so forth. And this is one trial. I was working with this one organic grower. And so I was asked him if we could do a fertilizer trial, and he was not planning to fertilize this block of lettuce because he was following snap beans, and he felt it was, the soil was rich enough and that the crop was going to grow fine. And so I asked if he could, well, if we could put out some little strips where we fertilize with the material, and he chose it and the rate. So he chose to put 400 pounds of this 1200, that's a feather meal. And it was incorporated into the soil, so it wasn't top dressed. And that's about close to 50 pounds of nitrogen. And you can see at the beginning at planting the soil, actually this is 11 parts per million. So this is actually lower than we would like to see. And then in the unfertilized plots over the course of the season averaged about 8 parts per million. And where we fertilized, it averaged quite a bit higher than that. And then when we got to harvest, we did see a difference in yield. The box weights were different. And the yield response was subtle, but measurable. And the take-home message I want to mention here is that this is a very experienced grower, and he had a good sense of how this crop was going to respond to fertilizer, and he was almost right. It didn't take very much. It just took a little bit of a boost to get this to the point where you got a little bit higher yield. And so this is just an interesting, I think, example of a grower, I think, who really had a good sense of his soil. And but sometimes these crops need just a little bit of a push to get a higher yield. But maybe 27 pounds per box was totally fine in his mind. And now talking about broccoli, now we start to talk about a whole different kind of crop. This is a crop, broccoli, it's a longer season crop, so 75 days to the first harvest, and it takes a couple of weeks to go through there and harvest all the broccoli. So it's out there a long period of time. And one of the things that we noticed about broccoli some years ago is that actually typical applications of fertilizer are about 180 pounds, but the crop is taking up 300 pounds. So it's actually scavenging nitrogen from the soil about 150 pounds. And if you look at the same data from the Regional Water Quality Control Board, what you see, here's the uptake range, 250 to 350 pounds of nitrogen. What you see, this graph is shifted to the left, where growers are routinely putting on less nitrogen than the crop is taking up. And so you got to ask yourself, this is quite significant. This is a lot of farms reporting here. So, and it's very common to see this. And kind of my sense of this is that this is a system that's evolved over time. The growers, they're seeing they're in rotations, double crop rotations, a lot of times with lettuce, prior crop or whatever, celery, spinach. And they have their skills, their observational skills have honed this system over time. They've watched their crops are growing fine. As long as the crops get off to a good start, then they tap into nitrogen deeper in the soil. And here's just an example. Remember I showed you that the spinach roots were more up here around the 15 to 18 inches deep at harvest. Here's broccoli. Their roots are down at 3 to 3.5 feet deep. And then here's just a picture of a root system that we dug a pit and observed these roots, and then also measured their density. And if you look at the density of these roots, they're down fully inhabiting the first foot, and then they're into the second foot, and then into the third foot of depth, and with a high density of roots in that second foot. And so what, turning to a couple of examples from organic, here is a couple of farms that we were working with. And in this example, the growers put on over 400 pounds of nitrogen. And both of these ranches were using top dress applications. And so the actual amount that mineralized from this was less than half of what they were applying. But they're in the ground for quite a long time, so that those mineralization from the soil organic matter actually turned out to contribute significant amounts of nitrogen. And so in the end, the crop took up, this crop took up close to 400 pounds. This one took up about 350. And then the total, excuse me, that was the available end. And then the crop took up about 375 and 325 pounds of nitrogen. So the crops were getting what they needed in spite of the fact that the fertilizer actually was pretty inefficiently applied. And so this is, I think, an example of, just one example of a crop that's out there for the, if you're growing crops that are in the ground for a long period of time, they actually are going to start doing things like scavenging nitrogen from deeper in the profile and so forth. And that's really quite an extraordinary thing that they do. And actually, if you look at, this is a study we did looking at, well, just how good is broccoli at scavenging nitrogen from a prior lettuce crop. What we saw, here's just 5 examples, but you can see that the broccoli is taking up, 80 to 90, almost 100% of what was left by the prior crop in the top 3 feet of soil. And then the examples where it didn't do that, here's on a sandy soil. This is a very difficult to manage sandy soil. And then in this example, there was just so much nitrogen there, the broccoli could only take up so much. And so it's an extraordinary thing that broccoli does, but broccoli's not the only crop that does that. I would argue that things like tomatoes do that. Peppers do that, other cole crops. And one of the things I want to point out, though, about the rooting aspects of a crop like broccoli and any crop is that here is a bunch of rooting depth data. Here's, in this case, we were measuring roots down to 10 and 11 feet. And those would be crops like Brussels sprouts and multi-pick kale that are out there over 200 days out in the field, and 160, 180 days. But the point of this slide is to show you, here is a Brussels sprout field where the roots did not go down. Here they are down at 10, 11 feet, but in this field, they only went down to barely 3 feet. And the reason for this is that if you have an impediment layer in the soil, so roots will, if they can go down unimpeded, they'll go down deeply. But in these situations, they won't, and then they'll be just more limited in terms of the resources that they make available to them. But the point I wanted to make about that deep rootedness is here is an organic farm that's been one of the old time organic farmers in this area. It's been organic for, well, it's over 30 years now since I took this slide, but we dug down 10 feet in the soil, and then we measured the organic matter all the way down. And what you see in the top foot, he had, close to 1.8. In the second foot, it was close to 1.4. And then in the third, fourth, and sixth foot, he had 0.8% organic matter. And what strikes me about this data is that it's showing that some of these deeper rooted crops can capture a good amount of nitrogen from deep in the soil, deeper in the soil, because this organic matter, I assume, is also liberating nitrogen, similar to this graph that Daniel showed on the first day of this series. You know, depending on the organic matter level in the soil, you know, 0.8 pounds of nitrogen per acre per day or 0.5. And then, but if you start adding that up over, you know, down to 4 feet or whatever, then it becomes a much more significant amount of nitrogen, kind of like what Joji was talking about with the strawberries. So this is something I think is an area that where we need more research, because we may be getting more nitrogen from deeper in the soil than we imagine. And then just 2 side thoughts before I conclude here. You know, one of the questions we have is how much nitrate is leaching in these organic systems? And one thing I should say is these studies that I did here in the Salinas Valley were of larger scale organic farms, and they are under the same economic pressures as the conventional farmers, where they have scheduling pressures, they have land rent pressures, so they're not using cover crops or compost any more than their conventional neighbors. But one of the things I'm curious is, do they have the same kind of nitrate leaching intensity that the conventional farms? And I would argue no, but I don't really have the data to back that up at this point. I have some little bits of inklings, but I don't have that data. And then also, what, you know, given the fact that they're not using compost or cover crops, you know, as much as you know they probably would like to do, what's the impact of the carbon-rich organic fertilizers on their systems? And one thing I just wanted to show you, like if we look at a typical compost application, let's say you're putting on 5 tons, and you discount it for moisture content, and then calculate out how much carbon is it applying. It's about 1 ton of carbon in that compost. A 7,000 pound cover crop will be putting on about 1.5 tons. But if somebody is growing 2 crops of spinach with 442 at 3,000 pounds each, it's putting on about 1,500 pounds of carbon. And 851, you know, if 1 crop of broccoli, if they're putting 5,000 pounds, it's putting on about 2,000 pounds of carbon. And the thing that it's part of the study that I was telling you about, we compared these organic farms with their conventional neighbors. And then we analyzed the soil for different components. And the one thing that jumped out, a couple of these indicators of microbial activity, the water extractable organic nitrogen in this FDA enzyme, they were both significantly higher in the organic farms. And so this is an indication that these fertilizers, carbon-rich fertilizers, are increasing microbial activity on these organic farms, in spite of the fact that they're not using a lot of cover crops and so forth. And but the implications of greater microbial activity is really quite striking, especially for nitrogen management, because they can help tightly couple the nitrogen. So just to conclude now, you know, given the complexities of fertilizer management and organic systems, we're kind of entering a new era of regulation. And so, you know, adding a cushion of extra fertilizer is going to be less and less of an option under these new regulations. And the thing that I kind of alluded to, that being a keen observer of how your plants are growing, how fast and so forth, because you're out there every day and you're watching them. So getting to know that, and I know you do, you know, those are key indicators to help you understand, you know, how is your crop getting the nitrogen that it needs? And then I think it's important to experiment, to put out a strip where you double up on the fertilizer, or a strip where you cut it in half and then watch. And if you can, evaluate the use of the nitrate test to see if it can help you manage your nitrogen. And then of course, irrigation management is hugely important, especially on sandy soils. And, managing nitrogen fertility in organic systems is more complex. And, the new regulations are going to be putting pressure on growers. And I think that we should be able, in organic systems, should be able to achieve compliance. I don't think that should be too much of a problem. But, doing everything that we can about, through good observation, through nitrate testing and so forth, are important. And then I think that, we're kind of entering a phase where there's more questions that we have about organic fertilization that we need to address. So I will stop there. And if anybody has any questions.
Yes, Richard, there are several questions for you.
Okay.
So shall I read that?
Sure.
Okay, first one, what testing method were used to determine that spinach needs 6 pounds of nitrogen per acre per day?
Okay, that was actually research that we were doing where we would go in like every week and take biomass sampling as the crop was developing. And then we analyze it for total nitrogen. And then we develop that curve. That's where all data falls on that curve that I showed there.
Great. The next one is, how common is fertigation in conventional vegetable system? Fertigation seems like one of the keys to improve nitrogen fertilizer management in organic vegetable production, if it be done economically.
Yeah, I think it's done to some extent, but it's not as common in vegetables because they're able to get out there and mechanically apply materials that are cheaper. The liquid materials, we're just now entering, just in the last, let's say 5 or 6 years, we've had the development of these hydrolysate materials that have less problems with plugging. But the table that you showed, Joji, shows the problem with them is just the cost, and so I think that's really the thing. It's not that they don't work, and it's not that it's not a good idea. I think it's just the growers are looking at the economics.
Great. Richard, many growers mulch dry pelleted fertilizers into beds right before planting spinach seed. Have you had a chance to compare yields for this approach compared to the top dress applications?
Well, I think that one little trial that we had where we had listed at listing and versus a top dress, and we had a little bit of indication there was a difference in yield there. One of the things when you say dry mulch, I mean, a lot of times those soils aren't entirely dry, coming around on the second, certainly the second crop of the season. So I think there is some mineralization going on in there. And they might let those fields sit for a while before they plant. They'll do it in advance, getting a block ready, and then they'll come in and plant on their whatever schedule they're doing. So, but there is a little bit of mineralization from those listed applications.
Great. Do you see differences in broccoli root depth when comparing seed planted versus transplanted broccoli?
No, we did not. We didn't have that much transplanted broccoli when we were doing those evaluations. I'm not sure how big of a difference you would see. but I can't say that I know. Sorry.
Okay, all right, a couple more. Why do you think cauliflowers scavenged much less nitrogen from the soil compared to broccoli?
I think cauliflower is just a much more sensitive crop, and they fertilize it more heavily. I think it's perfectly capable of scavenging, but to get the quality that they want, they fertilize it more.
Okay, so last question at this point is, in organic system that regularly incorporate compost and cover crops, what is the added value, if any, of applying high CN amendment?
Okay, that is a good question. In organic systems that regularly incorporate compost and cover crops, what's the added value of applying high carbon to nitrogen amendments? Well, the high carbon to nitrogen amendments are used in the fall. They have a specific use. And Joji, you chime in on this too, but they have a specific role to absorb that pool of nitrate that's sitting there in the just prior to the winter rains, basically. And that example that Joji showed was a beautiful classic example of what they can do. They can immobilize a large percent of that nitrate. If they get in contact with it, I think actually we could improve that graph of yours, Joji, if we had better incorporation. And then it, just like a cover crop, they get it through that wintry period and then into the next spring, when then you have all your opportunities to use it for crop production. So I hope that answers your question, Satya. If not, email me.
All right.
Okay, Joji, are we done? So
Oh, there's one more.
Oh, okay.
Oh, a couple more actually. Oh, thanks. Oh, one more. This is the last one. What is your opinion on additional substitute soil nitrogen testing, such as 21-day mineralizable nitrogen assay, or tests based on organic nitrogen forms, amino acids, sugars? Some have argued that soil mineral nitrogen tests based on KCl extraction only represent available and at the time and not soil capacity to release nitrogen.
Actually, if I could ask if Patricia or Daniel or Joji, if you guys would like to answer that question.
Yeah, I'm going to talk about it a little bit, but in my next talk. But yeah, so you're right that KCl extraction is just showing the snapshot of nitrate pool in the soil. So it's not necessarily it doesn't show the long-term availability of nitrogen at all. So other methods such as potentially mineralizable nitrogen and protein nitrogen and so forth can be better indicator for long-term nitrogen fertility.
Thank you. All right. Well, how about I introduce you, Joji, for the next talk. So now Joji is going to talk about frontiers in organic nutrient management. And we're looking forward to this, Joji.
Thank you, Richard. Yes. Okay, let me see here. All right. So my title is Frontiers in Plant Nitrogen Acquisition. And first, this is a typical, nitrogen dynamics in conventional systems. I'm just trying to illustrate how different between conventional and organic nitrogen dynamics are. It usually provides synthetic fertilizer, liquid synthetic fertilizers to apply in organic form, right? And then mostly nitrate and trying to respond to crop demand. Whereas organic systems mostly use the organic form of nitrogen. So always have mineralization or immobilization processes. So the inherently nitrogen management in organic system is much more complex than conventional system. Okay, with that, I put the figure from soil quality website of Australia, actually, showing some nitrogen supply, soil nitrogen supply. And as I mentioned briefly in my first talk, organic nitrogen, 98% of that nitrogen in the soil, mineralize and then release some mineral nitrogen, and then provide available nitrogen to crops. And then during this workshop, first Daniel talked about the mineralization of soil organic matter, crop residue, and amendment nitrogen. And Margaret talked about the nitrogen from cover crops. And Louise Jackson talked about the role of soil microbes in providing plant available nitrogen. And then Michael talked about nitrate in irrigation water. And Patricia and Margaret talk about nitrogen from organic fertilizers and compost. So we haven't talked about much so far is the this part. A small portion of organic nitrogen can be taken up by plants. This has been long been focused among organic communities. And so what's the science at this point? So let's take a look at it. Direct uptake of organic form of nitrogen by crop plants. This is one study done by Japanese scientists, published in 2000. And they did a very simple study, a greenhouse study, and then growing different crops, green pepper, leaf lettuce, carrots, and chingensai pak choy, with the either chemical fertilizer, ammonium sulfate, or rapeseed cake, organic fertilizer, in the same nitrogen rate applied, and no fertilizer, nitrogen at all. And then this is the nitrogen uptake. So pimento and leaf lettuce, ammonium sulfate provided highest nitrogen uptake, which makes sense because rapeseed cake has to be mineralized, right? So probably 60 to 70% mineralization. And then nitrogen is absorbed by plants. So the second was rapeseed, and control is the lowest. However, in this case, carrot and chingensai absorb more from rapeseed cake than ammonium sulfate. And spinach also shows similar trend with chingensai. So what's going on? So they did a series of studies and found some really large molecules of nitrogen compound was actually in the xylem sap in chingensai and spinach. And chingensai is this chart. And then let's see. This peak is actually from xylem sap. And then the darker peak is from soil. And then this peak was only found in chingensai and some other crops. So they got the evidence that some large molecules nitrogen that can be extracted by phosphate buffer was found in the plants. And then that seems to happen, not just mycorrhizal plants, which I'm going to talk about in a minute, but even in non-mycorrhizal plants. But so far, it's just a qualitative evidence only. And then the contribution of this molecular nitrogen uptake to overall nitrogen uptake is still unknown. And that seems to be the case for most of the organic nitrogen absorption study. It seems to be very difficult to quantify its significance of this function. So how about the soil plant microbe interactions in plant nitrogen uptake? And mycorrhizae symbiosis increased nitrogen uptake here. And arbuscular mycorrhiza present in 92% of plant families, and it can extend root. It's fungi, but by colonizing roots, it can extend the root zone and protect plant from pathogens and from extreme environment, and assist communication between plants. That's kind of interesting. And in California, it's been demonstrated that mycorrhizae can increase crop nitrogen uptake, including nitrate, and also reduce nitrate leaching and nitrous oxide emission, and relative nitrogen contribution rate. But relative nitrogen contribution rate is still unknown. And this symbiosis seems to be going for many, many years. There's evidence, fossil evidence that suggests that more than 400 million years, this relationship been taking place. So we just scratching the surface. We started to understand those, interactions between mycorrhizae and plants and soil organisms and so forth. But they've been doing this for many, many years. Another interesting fungi is called dark septate endophyte. Can also colonize in the plant roots and assist absorption of organic molecules, such as amino acid here. In this experiment, researcher compared the infected and colonized and non-colonized plants. This is Chinese cabbage, so it's not mycorrhizal. And then apply different kind of nitrogen sources, nitrate, ammonia, and then different kinds of amino acid. And in some cases, colonized plants absorbed more amino acid than non-colonized control. And this one was interesting, and my colleague and friend Tom Whaley sent me this paper for today's presentation. Thank you, Tom. And then lysophagy cycle. I didn't know about this, so I really thank Tom. But the interesting thing is microbes enter root cell from here, and then nutrient extracted from microbes by reactive oxygen produced by the plant cell. And then microbes come out of the root hair, and then microbes recharge with nutrients in rhizosphere. And cycle, repeats. This kind of phenomena has been observed for recent years, but again, precisely what nutrients are transferred through rhizophagy, or how important this process is for nutrient acquisition is still unknown, according to this paper. Another interesting thing is it's called rhizosphere priming effect. It is known that plants release up to 40% of photosynthesized carbon from roots as exudate. And usually soil microbes are carbon limited, so it's very hungry. And then as plants release carbon, microbes go there and feed on it. So microbial activity around the root zone is much more active than bulk soil without roots. So that can stimulate soil organic matter decomposition or sometimes suppression around rhizosphere. The definition of rhizosphere priming effect is the stimulation or suppression of soil organic matter decomposition by live roots and associated rhizosphere organisms when compared to soil organic matter decomposition from rootless soils under the same environmental conditions. So, data was highly variable. For carbon, negative 50% to positive 350%. And for nitrogen, the study using soybean and sunflower shows 36 to 52%. And it seems like it depends on the climate, plants, and soils. And recent published paper shows the rhizosphere priming effect of different crops like broccoli, lettuce, spinach, maize, and sunflower, with and without fertilizers. And the data shows when it's fertilized, it has more rhizosphere priming effect for broccoli, lettuce, and spinach. But one thing about this study, this effect, is mostly studied using pot experiment, because this is hard to do in a field scale. But due to the limited rhizosphere in the pot, especially under fertilizer experiments like this, the root density in the pot area might be higher than field condition. So probably this number may be overestimating. So I asked the author, actually the professor at our department, and Wei-Xin Chen is the one of the pioneer and authority of rhizosphere priming effect. So I asked him, it can be overestimated, and he said he agreed to some degree. But even other studies shows positive RPE in nitrogen. So there are some, but I don't know if this number is realistic. Also, this study used the UCSC farm soil. It's been managed for organically more than 20 years. So that could be a part of the high RPE effect as well. And lastly, I'm going to talk about the tightly coupled nitrogen cycling. And I mentioned briefly, and Richard talked about it too, but I think, in my view, this is one of the most groundbreaking work in the past 20 years or so in nitrogen management in organic systems. And Tim Bowles, first author, is a professor at UC Berkeley now, but this was his PhD work at UC Davis. Advisor was Louis Jackson. They surveyed 13 organic Roma type tomato fields on similar soil type in Yoro County, and found 3 patterns of nitrogen cycling. The first group is soil nitrate level throughout the growth season was low, and the plant nitrogen percent, tissue test nitrogen, was also low, and yield was low. So it's like nitrogen deficient. And the second group was opposite. Nitrate level in the soil is high throughout the growth season. And the nitrogen content in the tissue is high, and yield is high. So that makes sense. But the third group is interesting. Soil nitrate level during the growth season was pretty low. However, plant tissue nitrogen was high as second group, and yield was even higher than second group. So what's going on? That shows the 3 different patterns. The first one was nitrogen deficient, low yield, low soil nitrate pool. And second one is nitrogen surplus, high yield, high soil nitrate pool. And third one is tightly coupled nitrogen cycling, they call it. High yield, low soil nitrate pool. The third one, what's going on there? Their pool, soil nitrate pool was low, but nitrate flow was high, which means turnover of soil microbes and organic matter was pretty high, and efficiently providing nitrogen to active plant roots, tomato roots. So it doesn't accumulate in the soil, constantly providing nitrogen to the plants. That's why they call tightly coupled nitrogen cycling. And then those kind of field tends to have higher soil organic matter and the greater biomass of microbes. And then management-wise, they tend to have different stage of organic matter, fresh, decomposed, and medium and old, and different kinds of stage, so that providing nitrogen constantly. And then I talked to Louise Jackson about this the other day, and she said something very interesting and intriguing. Amazing thing is that these growers developed this tightly coupled system from experiences. I thought, finding this phenomena is wonderful and then great discovery, but she applauded the growers who made this, and I totally agree. And I think one of the important roles of scientists, agriculture scientists, is to learn from pioneer organic growers, document it, and discover the principles and share with others. And then also Luis told me the other day that tightly coupled nitrogen cycling idea came from her postdoc study at UC Berkeley. She studied the nitrogen dynamics in California annual grassland. This is a paper she wrote. And then in which she found very similar things. Let me read here. Plant accumulation of nitrogen was mainly confined to 2 short periods of the year, fall and early spring in the California grassland. At these times, plants were in a vegetative growth phase, roots were growing rapidly, and soil moisture was high. During these periods, soil nitrate was low or depleted. High flux of nitrogen in this ecosystem, however, is indicated by the rapid disappearance of the previous year's detrital material, high microbial biomass, and high mineralizable nitrogen and nitrification potential. Doesn't it sound familiar? So in some sense, Luis started this work from the beginning. Throughout her career, she demonstrated that we can learn nitrogen management from natural system in California. And I think this is so important, at least to me. Agroecology always talk about mimicking nature, but this is a really good example of how to learn natural system and make agroecosystem management more sustainable. And lastly, I found this paper, a review paper in Plant and Soil, very intriguing, past, present, and future of organic nutrients. It's a fascinating review paper published in 2012 about organic nutrient acquisition by plants. The conclusion is, after decades of focusing on inorganic nutrients, perspectives have greatly widened again. As has occurred before in agricultural history, science has to validate agronomic practices. We argue that the framework that view plants as mixotrophs with an inherent ability to use organic nutrients via direct uptake or aided by exoenzyme mediated degradation, will transform nutrient management and crop breeding to complement inorganic and synthetic fertilizers with organic nutrients. And this review contains lots of historic development of organic nutrients study and inorganic mineral series, and even how USDA changed organic nutrient study right after World War II. So Eric Brannon, if you haven't read this paper, I'll send it to you. So with those, a lot of uncertain and but fascinating nitrogen acquisition routes, I modified the organic nitrogen management dynamics in organic system a little bit. I added mycorrhizae and the endophytes. We don't know how much they contribute to it, but so it's quite narrow, but rhizosphere priming effect and so forth. Not just mineralization, immobilization. So lots more research needs to be done. That's it, thank you.
Very good, Joji. Thank you very much. So we have a question for you. Are there any accessible methods available for measuring soil microbial biomass?
Accessible method, I don't know what it means, but there are methods to measure soil microbial biomass, but they use, usually use the chloroform and so forth, and basically fumigate the soil and then see how much it's gonna be mineralized after fumigation. Yeah, there are methods, but still it's not commercially available, I don't think so.
Okay. Here's one. For the Bowles tomato study, could it be that the group of growers with fields of higher N use efficiency could also have had better irrigation and other management practices, therefore tight overall management and not only tight N cycling, consequently
Yeah,
higher yields?
yeah, absolutely. Yeah, irrigation improvement is going to be very important.
Okay. By the way, if anybody has any questions for Daniel and Patricia and Michael and Margaret are still here. You know, feel free to ask questions of any of the speakers from the prior session. So Joji, just a question for you about the you know, the microbes interacting with the soil. Do we know what those microbes are, or is that something that's not determined yet at this point?
With the soil, which one?
Or the ones that are getting the rhizosphere and that might be providing beneficial access to nutrients and that sort of
come
thing.
out of the roots and yeah, lysophagy cycle. Well, I just learned that, you know, paper, so I'd be happy to share with it, but I'm not sure the detail. Yeah, please email me and I'll send you a paper.
Mm-hmm. Okay. But those organisms, they are basically benefiting from carbohydrates that are exuded from the roots, and then they live there, and then and do whatever it is that they're doing.
Yeah. That you know, mycorrhizae and endophyte. Yeah, that's the case. You know, receive carbon from plants and provide something else in exchange. And you know, bacteria entering plant roots and coming out. That I don't know. That's detail of that just yet. So, but usually that's the case.
Uh-huh. And then just one final thing about that, because that's a fine line between a pathogen getting in there.
Yes.
Like Phytophthora, Pythium, or
right.
You know, those kinds of.
Yeah. So it seems like plants, you know, have sent a chemical signal to attract some beneficials and resist some pathogens. And those details are started to be, you know, understood, but we are still at early stage, to my knowledge. It's a very fascinating area of research, you know, how they communicate each other. And there's a term proposed like a rhizosphere immunity. You know, plants have some immune system to resist pathogens, but plants also release exudate to facilitate the resistance system using microbes. So root plants and also those microbes and plants interact with soil environmental factors. So including all of them, the concept of rhizosphere immunity has been proposed. So it's fascinating.
Mm-hmm. Yeah, I mean, I think it really gets to the point that we still have a ton to learn about
yes.
Plant nutrition, and I think things are going to evolve. We have a batch of new researchers coming into this area, which is wonderful to see, and so there's a lot we can learn. Here is another question. Where did it go? Oh, okay, here we go. In the tomato study, did the authors identify specific management practices linked to having tighter nitrogen cycling?
Yeah, so as I mentioned briefly, the grower tend to use different kinds of organic amendment, like, you know, plant-based, yard-based compost and the fresh cover crop residues, and so different kind of organic amendment has been involved. And then as needed, also they use the liquid fertilizer, organic fertilizer too. If I think that's the case.
Okay. All right. Well, let's see if there's any other, oh, here's some in the chat. Let me just see what's going on here. Okay, here's one that came in on the chat. Sorry. Because we were dealing with an audio problem in the chat. So, okay, regarding Moss Bittner's question, are there any accessible methods available for measuring the soil microbial biomass? This recent paper showed that microbial biomass is highly correlated to simpler measurements like a modified slate test. And then here's my tweet on this that has a link to the paper. And so this is from Eric Brennan. And so go to the chat to get to that link. But what's your answer to his questions, Joji?
Yeah, thank you, Eric, for helping me. Yeah, I didn't know that, so yeah, please check Eric's information.
Okay, and then there's a link to the paper, and it's open access. And then there's a repeat of that question. Let's see. Yeah. Okay. I don't see another question. That was the question. So, all right. Well, let's see if we have any more. I think there's one more that just came in. Oh, it says thank you. Okay, folks, I think, oh, let me check the questions over here. This is complicated. You guys are making me work hard. No new questions there. All right, I think we have saturated the audience, Joji, and we want to thank all the participants in this series, all the presenters, Margaret and Daniel and Louise Jackson, and then last week Patricia and Michael and Margaret again last week, and Joji. Thank you very much. So if people have any further questions, email the presenters, and then Rachel has some final things here to talk about.
Also, thanks to Diego for translation.
Oh, of course. Yes, thank you for remembering, Joji. Yes, Diego is over there quietly doing a wonderful service to our Spanish-speaking audience. So thank you, Diego Chelis, for your presentation, translation. Thank you. All right, so Rachel?
Yeah, I think that pretty much covers it. Thank you, Diego. And here's the QR code if you need a certified crop advisor credit. I'll send an email out by 5 p.m. today. So keep an eye out for that if you don't have the CCA app. And yeah, thank you so much for being here.
Okay, thank you everybody for being here. And like I said, contact us if you have any follow-up questions. Have a good day.